Ultrafast Laser Summit. Thank you all so much for joining us. And in this session, you'll hear from Christian Gaida, the head of research and development at Active Fiber Systems GmbH. Christian earned his doctorate in 2019 for his work focused on high power fiber laser systems. And today, he joins us to highlight advancements in 2 micrometer high power fiber laser systems. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's sessions, you can always come back later and watch them on demand. That's all from me. Christian, we appreciate you for taking the time to join us here at the Ultrafast Laser Summit.
Okay, Jake, thank you so much for the kind introduction. My name is Christian Gaida. I'm with Active Fiber Systems, and today I'm delighted to talk about advances in 2 micrometer high power fiber laser systems. Before I start with the real content of my talk, I would like to introduce our company. Active Fiber System is located in Germany, in Jena. It's also called very often the city of photonics. We are working with fibers, as our name says, and we have developed very high power femtosecond laser systems. But now we are also working on some other exciting stuff that I will talk about here. We were founded in the year 2009, and since 2022, we are part of the Trumpf Group. We are now around 100 employees, and we are growing rapidly. Our core technologies comprise large pitch fibers. I will talk about this a little bit more in detail later on. They can be ytterbium doped or thulium doped, and ytterbium doped fibers typically emit at 1 micrometer wavelength, and thulium doped fibers emit at around 2 micrometer wavelength, which is the topic of this talk. But then we are also into coherent combining of many fiber amplifiers. And also we developed multi-core fibers, which will be the bright future, as we think, for fiber laser systems. And then we have some add-ons in our portfolio, like post-compression of ultrafast pulses, all the way down to the Q cycle regime, or even very exciting applications like high harmonic generation towards the extreme ultraviolet wavelength regime. And of course, with these type of systems, we can use those lasers for very exciting applications like pump probe experiments or imaging applications in different wavelength regimes, spectroscopy, and in the industrial case, at 2 micrometer, for example, for material processing. And depending on the application, we require different parameters. So the size of the system will also change. So you can see here 2 examples. One is a very powerful system, a real beamline, which consists of a laser and post-compression, and then also an extreme ultraviolet source. And in contrary, you see here also an industrial laser system, which is much smaller and of course less powerful, but it's then of course used in a different environment. So on the one hand, scientific use, research, on the other hand, industrial use. So this brings me to the core of active fiber systems, fibers, general properties of fiber lasers and their concepts. And I just would like to give you a very brief introduction here. How does light guidance work in a fiber? So when you think of a fiber, it's basically a structure with an index step. It can be made of glass, for example, and this index step allows the fiber to guide light. And the mathematical description is to have eigensolutions there, which are fiber modes, which are describing the guiding properties of these fibers. And if you do everything right, make the index step very small, you can achieve only the guidance of the fundamental mode. And this is very interesting because if we use this core for the signal light, we can have fundamental mode operation, and we can have a second core where we guide the pump. And in this case, the pump will be absorbed and the signal light can be amplified. And this is very interesting because we can use low brightness pump light and high brightness signal light that's amplified. So a fiber amplifier is something like a brightness converter. And that's very, very exciting because we have advantages like diffraction limited beam quality for the signal light, and we can have very high efficiency due to the length of the fiber and the nice core size to length ratio. And we have, of course, also very good heat dissipation because we have a large surface to volume ratio. Although we have many advantages, there are also some significant challenges with fibers when we use them as amplifiers, particularly when we use them for pulse amplification. And these challenges are typically associated with nonlinear effects, for example, self-focusing or self-phase modulation, which are both correlated to the Kerr effect. So, and there are some ways to mitigate this, especially when we operate in the ultrafast regime. And many of you probably know this. There's the chirp pulse amplification technique, where we use an initially very short pulse as a seed pulse. We stretch the pulse, then amplify it and recompress it later on. There has been a Nobel Prize for this technique, and it's used for many ultrafast lasers worldwide. And when we look at the nonlinear phase that's accumulated during the amplification, you can recognize in this formula here for the B integral that when we reduce the peak power, we can achieve a significantly lower nonlinear accumulation. But this is not the only effect that we can play with. We can also look at the length and the area of the signal light that's amplified. And this is where advanced fiber designs come into play. And in this case, the so-called large pitch fiber. And large pitch fiber is a specific design. It's not a step index guiding mechanism. It's more like a mode filtering effect. And we have a preferential excitation and a preferential gain of the fundamental mode and can achieve very large mode field areas. And this mitigates nonlinear effects, of course. Also, due to the large core, we can achieve very short lengths of those fibers, again, mitigating nonlinear effects. And at the same time, maintain the diffraction limit beam quality, which is very important. Okay, so this is one mitigation strategy. Nevertheless, there are some effects at some point when we amplify a lot, which will occur, like fiber facet damage or even, again, nonlinear effects, which will limit our amplification capabilities in those fibers. And we can have thermal issues, which is shown in this video, that at some point the thermal heat load is so high that the fiber will simply burn. And there are some real thermal issues, which are called mode instabilities, where the fundamental mode, the Gaussian-like mode, just disappears and we have an ugly higher order mode, which is not usable anymore. So what can we do about it? Well, we can accept that we can only, to some extent, use mode area scaling to reduce nonlinear effects. And at some point, we will face physics related damages or limitations, and we can only use parallelization techniques to further scale the power of our laser systems. And we have one very interesting technique to do that, and it's called coherent beam combination. And how does this work? So basically, it's like a CPA system. You start with the front end, you stretch the pulse, and then you divide your pulses into several stages. And in each stage, you have an amplifier, and then you amplify those individual pulses, recombine them in a combining stage, and you have basically n times the power of an individual amplifier. And this works through interference, meaning you have a phase adaptation between the different amplifiers. So the path length differences is minimized and also controlled so that we always have coherence and positive interference effects. Yeah. So in this way, we can basically scale the power by a factor of n, with n the number of amplifiers. Yeah, and fibers are obviously ideally suited for this purpose because they have a great beam quality and are very similar to each other. Okay, to sum up, the achievable laser parameters for coherent combination are only limited by cost and size, but not by laser physics of the individual amplifiers. So that's a great news, but it makes those systems potentially very large. Here you see a combining system consisting of 16 of those fiber amplifiers. You see the beam division stage, then you have an amplification stage, as I just mentioned, and the combination. But those systems are very powerful, but also complex, and they get relatively large. And of course, when we ask the question, what's next, I also already mentioned multi-core fibers can actually help us to reduce the size of those systems while maintaining this excellent scaling properties. Okay, so let's jump into the 2 micrometer field. I've already mentioned that there are different dopants for fibers. It can be traditionally ytterbium, where we operate at 1 micrometer wavelength. And when we want to go to 2 micrometer wavelengths, we have to dope with thulium or holmium. In our case, we chose thulium, and this is because thulium has very exciting properties which can be useful for high power amplification. First of all, we have a very broad amplification bandwidth in the 2 micrometer regime, which also supports sub 100 femtosecond pulse durations. Then there is 790 nanometer diode laser technology, which can be used as a pump source. This is very exciting because it's an easy way to pump thulium, although we have typically quite a strong quantum defect heating. There's a trick to get around this quantum defect heating, and this is through cross-relaxation processes. So you can imagine it like this. You have one ion which is excited, and you have a neighboring ion which is excited in parallel by a de-excitation of this original ion. So you can boost your quantum efficiency almost by a factor of 2. This trick works, so you can basically achieve double the efficiency, but it's sometimes difficult to achieve it, especially when you want to go for high energy extraction, as this typically requires a very high inversion level of your laser. One way to get around this is the called in-band pumping technique. It's an efficient alternative. You can directly pump the laser in-band, in this case, reducing the quantum defect by a factor of 2. And this is, of course, a very powerful option to scale the average power while simultaneously extract high pulse energies. What are other challenges associated with 2 micron? When you look in the 2 micron wavelength range, you can recognize significant water vapor absorption lines in the atmosphere. And this has some consequences, and I will talk about this now in a little detail. We have significant overlap with the thulium gain bandwidth, and this has some consequences in the spatial as well as in the temporal domain. Here in this video that I'm about to show, we have done a testing with a continuous wave laser at 25 watts of average power, and we have scanned over those absorption lines with a narrow line width. And what you can recognize is when we scan over those absorption lines, the beam shape that's originally Gaussian-like and very nice becomes very ugly. Yeah. And this is an effect that we cannot avoid. It's called thermal blooming, and it happens due to the heating of the air during the propagation. Another effect that I've also mentioned is the temporal effect. So due to the absorption lines, we will have also a phase effect on the pulse, which transfers pulse energy in a pulse tail. So through the Kramers-Kronig relation, each absorption will also cause a transfer of energy to outside of the main pulse. And this is shown here. So due to this formation of this pulse tail, we will have less peak power and an ugly pulse contrast. Both effects are limiting in ultrafast system particularly because there we cannot avoid those absorption lines. So that means in order to operate at high average power and high pulse energy in those thulium systems, we need to get around those water absorption lines. The obvious conclusion here is, okay, we need to go to vacuum or need a dry atmosphere in order to get to operate the system at high average power and high peak power. Or we can choose the long wavelength side of the amplification bandwidth of thulium to avoid those absorption lines as much as possible. This is something that we do, for example, for smaller systems like in the industrial field, but it will also increase your achievable pulse duration. Let's now jump into our scientific ultrafast 2 micrometer fiber lasers. As I've just mentioned, in order to achieve very short pulse durations, we need to cover a very broad spectrum. And this requires those systems to become compatible with vacuum or even dry atmosphere for highest average powers and peak powers. So why is it interesting to develop those systems? When we think about the traditional ultrafast laser systems at 1 micrometer wavelength, we can see that we can also cover other wavelengths. For example, through different frequency generation, we can start with a 1 micrometer pump and go towards the mid-IR, or we can use with the start with a 1 micrometer pump and use harmonic generation to achieve shorter pulse, shorter wavelengths. And this can be very interesting for imaging, spectroscopy, and so on and so forth. Now, if we start with a 2 micrometer pump laser, we can actually extend the wavelength range, and this will enable new applications. If you look towards the mid-IR, we can access the interesting fingerprint region, which is interesting for spectroscopy or imaging in the range of molecular biophysics, for example. Now, at the same time, it's a little bit counterintuitive. You can go use harmonic generation with the 2 micrometer driver and actually reach much higher photon energies or much shorter wavelengths, which can be interesting because you can enter an exciting regime within the water window where where the radiation becomes transparent for water, but you can look at, for example, living cells in the so-called carbon K edge. So it's interesting for imaging and spectroscopy in both directions, long wavelengths and short wavelengths, and 2 micrometer seems to be a sweet spot to drive those nonlinear conversion techniques. But since it's a nonlinear conversion technique, you have typically quite low conversion efficiencies. And in order to do imaging and spectroscopy, you need high flux. And high flux means you need very powerful drivers. So high repetition rate and high pulse energy, and ideally few cycle or few cycle pulses. So it's a very challenging regime of parameters that is required here. And we have some platforms that can actually deliver very powerful output pulses. Here is a single channel thulium doped fiber CPA system, which can deliver 50 watts and 0.5 millijoule of pulse energy with sub 200 femtosecond pulse duration. We also have the capability to make the system CEP stable. And you can see that we have an excellent beam quality here and a very short pulse. So this is a very good starting point for some of the things that I've just mentioned to go towards the extreme ultraviolet or towards the mid-IR, of course, with post-compression techniques, for example. And we have even more powerful systems where we use multi-channel thulium-doped fiber CPA systems, so using the combining technique, combining several of those amplification channels. In this specific case here, we combine 8 of those channels and achieve 200 watts and 2 millijoule of pulse energy with sub 150 femtosecond pulse duration. And this can be very challenging, and you see it here in this image that we are in a vacuum environment here, and this requires specialized fiber modules that can sustain the high heat load in the amplifiers while being in vacuum, and also for the long-term and pointing stability. Due to the fact that we are in vacuum, we also need optical alignment with motorized stages, so it's also a challenge for optomechanics. And in order to get an excellent pulse amplification and compression, we need to compensate for gain narrowing and control the amplitude and phase of the pulses. All this we have developed, and all this is still en route, but you can see already that these systems are used by our partners at the Fraunhofer Institute and the Institute of Applied Physics to achieve few cycle pulse duration in the 2 micrometer regime. And this is very exciting because with these high flux, high repetition rate systems in the few cycle regime, we can drive harmonic generation in the water window. And this will boost many applications in this field. Okay, so let's go to the ultrafast 2 micron fiber lasers for silicon processing, our industrial laser. As mentioned, silicon is the main target here because silicon is transparent in the 2 micrometer wavelength regime. So you can envision many different applications: bonding, debonding, dicing of silicon, wafer trimming, welding, or functionalization of silicon. And the parameters that are required for these type of applications are significantly relaxed compared to the scientific field. Here we are in the range of maybe a few hundred nanojoules to 100 microjoule, and the repetition rates ranging somewhere between single shot to 20 megahertz. The pulse durations depending on the application, should be somewhere between 500 femtoseconds and maybe up to 1 nanosecond, but really depends on the application. And we have built a system and designed a system that's capable of all this. So we try to really focus on the silicon processing applications. And the so-called Active 215, it's the name of our product, can deliver 400 femtosecond pulses up to 1 nanosecond pulse duration at 100 microjoule pulse energy, which is quite a lot for and sufficient for all the applications that I've just mentioned. The average power is moderate, it's only 15 watts, but it's in the long wavelength side of the thulium gain bandwidth, which relaxes the situation with the atmospheric water absorption. And of course, besides silicon processing, there are also other applications that can be interesting, can be plastic bonding, weeding, tissue removal, photovoltaics, and so on and so forth. Yeah. Worth to mention that this is the first active fiber system industrial system, also inspired by Trump technology, which features all the stable all-fiber designs, modular serviceability, and a compact, lightweight build for easy integration. And here are some performance data on the system. So we have operated the system here on our facility for more than 500 hours. But then we have delivered several of those systems to our customers, and several of them are now operated with more than 10,000 hours in a very stable regime. So more than 15 watts of average power, excellent pointing stability, so really for 24/7 operation and industrial use. Very important for many applications is also the intensity on the target. So each pulse needs to provide similar properties. And this is why we have worked a lot on reducing the peak-to-peak power fluctuations of our systems, and we achieve excellent values here with relative intensity noise smaller than 1% and a peak-to-valley fluctuation of less than 6%. And this is possible even with external triggers, so pulse on demand, which is very important for our customers and helps to provide very stable processing. And another point is the excellent focusability of the system and beam quality. And it's not only about the beam quality in terms of m square, so how diffraction limited the beam is, it's also the circularity, so that each spot looks similar with each laser system. And for the processing of wafers, for example, it's extremely important. And we have achieved a very stable regime here with excellent beam quality and very, very good ellipticity, a very round beam. Okay, so now let's come to my final topic, the 2-micron fiber lasers for driving extreme ultraviolet. And this is a little bit different topic because here we are not talking about ultrafast lasers. We are talking about laser systems for this very famous company, ASML, which use lasers for lithography, so wafer lithography and chip production. And as you all know, the AI development requires much more powerful chip industry. So we need to produce many chips in the near future, which means we need to increase the capabilities of those systems. This comes with two demands. One demand is we need more efficient lasers to drive EUV, and we need more powerful EUV sources. Currently, those systems are built with CO2 lasers, and these CO2 lasers are focused on tin droplets, which then generate the EUV. And the footprint of those systems is already quite large. And if we want to scale the power of those CO2 lasers, those facilities and those lasers need to become much larger. And the second problem is the efficiency of those systems, that the power consumption is just tremendous. So one way to get around this could be solid-state laser technology, particularly 2 micrometer. And the parameters required for this process would be very large. So we would have to go to pulse energies beyond 1 joule, and we would also have to achieve very high repetition rates of up to 100 kilohertz. So we are talking about up to a 100 kilowatt laser here. So why is 2 micrometer interesting? I've just talked about the efficiency of those CO2 lasers, and we need to think about the conversion efficiency. How efficiently can we get the extreme ultraviolet light using the drive laser? And the conversion efficiency up to theory and current research can be up to 5%, which is quite similar to the CO2 driving laser technology. Now, if you look at the wall plug efficiency of solid-state lasers, we can expect a much higher wall plug efficiency than with CO2 lasers of up to 20%. So there is reason to believe that from an economic point of view, 2 micrometer could be a sweet spot. The question is, do we have a concept to achieve these very high pulse energies and average powers? And there is a vision that we have that this might be possible using multi-core fiber technology. In this specific case, I've assumed here a 4x4 multi-core fiber. And if we assume that a single core could provide us with 5 millijoule of pulse energy at 100 kilohertz per repetition rate, we would end up with 500 watts of average power, always assuming diffraction limited beam quality. Now, if we sum this up to 16 cores, one of those amplifiers could provide us with 80 millijoules and 8 kilowatt of average power. Of course, we need to do a coherent combination in those multi-core fibers, but this might be possible. The question that we need to ask is it feasible to achieve 5 millijoule and 500 watts of average power from a single amplifier? And when we are still not there, right? So we need to combine many of those. In this specific case, we could envision that we could, for example, combine 20 of those multi-core fiber amplifiers, and this would give us in the end 160 kilowatt and 1.6 joules of pulse energy. So this is the vision. Question is it realistic? So in order to partly answer this question, I would like to present you our recent results on power scaling thulium fiber amplifiers. And the current status doesn't look so good. If you look in the previous or in the history of thulium fiber amplifiers, you can recognize in terms of average power, more than 1 kilowatt has been achieved, and in terms of pulse energy, a few millijoules have been achieved. But nobody ever showed the combination of both. And there's a reason for it. It's very hard to do because as I mentioned earlier, if you want to extract a lot of pulse energy, you need high inversion levels, and this will lower your efficiency. But here in this case, we need all three parameters at the same time: high pulse energy, high average power, and high efficiency. So our target regime is very difficult to achieve. So we have done some testing. So we have built a nanosecond seed system, which provides us with pulse durations somewhere between 20 to 600 nanoseconds and pulse repetition rates of up to 400 kilohertz. And then we boost these pulses to an average power of around 20 watts. And then we have two different fiber types, the large pitch fiber and the photonic crystal fiber that I've already mentioned earlier, which provide us with very large mode field area. The one fiber is a rod type fiber. The other fiber is a fiber which is bent and up to 6 meters long. And I would like to briefly show you our recent results. So with a thulium large pitch fiber, we have achieved up to 9 millijoule of pulse energy and more than 500 watts of average power, and at a very high efficiency of 75%. And this is due to the fact that we have used an in-band pump here instead of a 790 nanometer pump. We also looked at the stability of the system. It was very good. So it shows us that we are capable of more than 5 millijoules and 500 watts, even in a long period of time. I think, of course, it's still under development, but it shows us the potential of this technology. Now, if we look at the thulium photonic crystal fiber, which is much longer in length and the heat is more distributed along the fiber amplifier, we also used the in-band technique, and we achieved more than 1.4 kilowatts of average power from this type of fiber. And this is, up to our knowledge, the highest reported average power from a 2 micrometer fiber laser to date. So these are very exciting results. And if you look at these, the graph that I've shown you in the beginning, that where our target regime is. And we asked the question, can we achieve 5 millijoules, 500 watts, and 80% of slope efficiency simultaneously? The answer is yes, we can. We have shown more than 9 millijoule of pulse energy and high slope efficiency of 80% and almost 1.4 kilowatt of average power. So, and this being said, it's a power scalable concept due to the high brightness of the pump lasers that we used. So, are you ready for the next step? If you would like to partner with us to develop your high power fiber lasers, let me know. I was very happy to give this presentation, and I'm happy to answer all the questions that you might have. Thank you very much.
And Christian, thank you for teaching us about advancements in 2-micron high-power fiber laser systems. Just to echo your statement real quick to everyone that's joining us in the audience, if you haven't already, you can type your questions and comments into the Summit chat box. And do not worry, if you have not been answered yet, you will be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Ultrafast Laser Summit. Thank you all so much for joining us.